All right, can everyone hear me?
Yeah.
All right, so now for something very different. So I mentioned yesterday that after September 11th, I was at the Naval Research Lab in Monterey working on coupled air-sea modeling, putting the pieces of the COAMPS system together in research mode, applying it to the Adriatic as part of a field campaign with the NATO Undersea Research Center funded through the Navy. And after 9/11, I felt compelled to make my work more relevant to national security. So I received a science fellowship to be a visiting fellow at Stanford Center for International Security and Cooperation. And I opened up a new research direction in my work, and that was focused on connecting coupled air-sea models together with high resolution building resolving models for contaminant transport in urban areas. So what I'm going to do today is give you some highlights from that, several aspects of that work, that trajectory that I think might appeal to you as an application that has some intersections with what you all do. But I think there'll be a lot that's new for you as well, since it relates to airborne transport. So what we did with COAMPS, and we talked about COAMPS yesterday, is what we did with COAMPS is introduce an urban canopy parameterization to take account of the fact that the buildings modify the atmosphere overlying the buildings, and they modify it in several different ways. But for instance, for New York, which is the city that we focused on the most, the building landscape, those of you who've been to New York know this, it's quite a striking urban morphology. It has very tall buildings around Midtown. So this is the island of Manhattan, has very tall buildings around Midtown and very tall buildings in the financial district or downtown. And in between, that's relatively flat. That's the West Village, the meatpacking district. So what that looks like in transect is if you take a transect from north to south, that's shown here from north to south. You can see those tall buildings in Midtown and tall buildings in Lower Manhattan and these relatively flatter areas on either side. So we introduced an urban canopy parameterization and nested down to about 300-meter resolution in order to capture some of the ways that the city impacts the meteorology. These are the equations, the ways that it modifies the physics happen in terms of the momentum equations and heat transport. The city gives off heat, and so there's an anthropogenic heating term. Another key factor is the building heights, the average building heights, the variation in the building heights. So these are some of the things we'll be looking at in several of the subsequent highlights that I'll give you. But first I want to take a step back and show you how this model can be applied to an application related to heat waves. So this is the same COAMPS weather model with an urban canopy parameterization for New York City. And this is work that my recently graduated PhD student finished looking at the evolution of heat waves in New York City. So in New York, we've been subjected to an increasing number of heat waves. And they can be quite severe in our area because parts of New York City don't have air conditioning. And we can be subjected to power outages as well. This is a heat wave. We had two extreme heat waves, heat events in 2011 in June and July. And this particular one is showing you the evolution of the heat wave from the COAMPS model. And one of the things that's interesting about it is this strong gradient between the air temperature over the ocean and the air temperature over the land, and the heterogeneous nature of the evolution of that high heat event, particularly in urban areas. And you can see that also manifested in the winds over time throughout the day. In particular, the sharp coastal gradient between the strong winds offshore and weaker winds onshore, particularly when the sea breeze kicks in the afternoon. And so what my student Tallmeyer did was set about to evaluate the COAMPS model in terms of the available observations and look at the footprint of the heat wave on the city. So here's a picture from that showing that sea breeze development. And now here are these white lines are the observations of the winds overlain with the COAMPS for the two different heat events, the one in June and the one in July. This is 1 kilometer COAMPS nest. We're looking at the 10-meter winds over the heat wave. And for reference, compare this with the 12-kilometer NAM, which is a coarser resolution model, and you can see the impact of gaining higher resolution. In particular, you better resolve that coastal gradient that I mentioned compared with a coarser resolution model. And it better aligns with the observations as well, these white lines. Why does this matter? Well, it matters because we're set to see an increase in heat waves in our region. This was a study that came out a few years ago showing against the background or reference state of heat waves, what's projected in the future and the difference. So in terms of three metrics, heat wave intensity, heat wave duration, and heat wave frequency, we are set to see an increase in our area along the eastern seaboard of the United States. So heat waves will be a challenge that we will continue to face in the U.S. with potentially more devastating impacts. And I think that you all similarly are set to receive more heat waves as well. And it's an area that requires increased attention from society and science. So I want to transition to another application, which is transport and dispersion in the atmosphere. So this is a slide to sort of motivate this part of the presentation, showing a release of a smoke plume into two different levels in the atmosphere. And this is a classic photo. They go in opposite directions. So how do you make sense of that if you're talking about an airborne contaminant that might cause harm to a population, either urban or rural? You have to be able to predict where it will go and potentially be able to warn and evacuate people. But the inputs to the models that you use really make a difference in terms of what you get out of the model. So this is an example that uses the Defense Department's HPAC model, which is the standard atmospheric transport and dispersion model that was developed by our Defense Department, but is also now the national capability for domestic incidences. So it's been embraced by the Department of Homeland Security. So it will be used both for international and domestic events where there's a transport of a contaminant. And what this slide is meant to show is if you take the National Weather Service network of observation, shown here with these arrows, and you, for a given moment in time for the Chesapeake Bay area on the east coast of the US, if you produce a plume plot from that, it goes in this direction. If you augment the backbone of that National Weather Service network with a mesonet or a more highly refined in space observational network of meteorological stations that you can see the distribution here, and you produce a plume plot based on those observational inputs, it goes in the opposite direction. And so the impact of having increased observations is clear. But you don't always have a lot of observations, and especially in places where it matters. We are challenged by a lack of observations, actually, in some of our most densely populated urban areas. So what's the standard operational response? Well, the operational response is to use a nested model and give the model output to the transport and dispersion model, and then produce a plume emanating from a source based on the meteorological model forecast. So that's the standard that's used by the current operational community. So why does it matter? So why do we have to think in different ways about urban populations versus out in rural areas? So imagine you have a threat scenario. This is the East River of the US. You have a small vessel delivering some sort of dirty bomb or contaminant to New York City. So this is the East River. This is the helicopter pad where a lot of dignitaries arrive for the United Nations or the president arrives. So what would happen to a contaminant plume coming out of that source? Where does it go and who needs to be evacuated? Well, if there's offshore flow, the contaminant would stay near the ground, near the river, and propagate out towards Brooklyn. If there's significant mixing, it would just be transported up into the higher parts of the boundary layer. Or if there were flow directed toward Manhattan and mixing in the urban area, you might see a ventilation of the city by this contaminant. But it really is this complex interaction of the 3D structure involving the atmospheric stability, turbulence, and the winds. So imagine there's no urban area there at all. This is a green pastoral region like when Manhattan was first founded. Imagine deer and frolicking rabbits. And so if it were a nighttime release, there'd be a land breeze. So the winds would be coming off the land. There would be high stability in the atmosphere, low turbulence, and the plume would just drift off over the East River. But now imagine the winds are directed toward the city and you get all kinds of very complicated interactions of the contaminants with the urban environment. And some of the things we've seen are recirculations in the lee of buildings, pressure-driven transport up the side of a building. And so it gets, the contaminant gets drawn into an area of the boundary layer that's swifter so that it could get transported many blocks downwind and get deposited in another entirely different neighborhood. We also see significant channeling down streets and penetration into surrounding areas away from where the immediate release occurred. So there's also strong sensitivity to the time of day of the release, as you can imagine. These were just some simulations we did with COAMPS looking at several different release sites at several different times of day. And you can see the complexity in the flow and the transport patterns. And some of these times the city would be spared, and other times the city would see a significant transport of contaminant. My PhD student, as her final paper, used the same Defense Department DHS tool for transport and dispersion problems and looked at the sensitivity of the release site to the wind direction and the proximity to water. So what she did was choose different release sites in the Manhattan area. So this is Manhattan, this is New Jersey, this is Staten Island, Brooklyn, and Queens. So these red dots show you the release sites chosen, and they're all rather near the water. And these lines show you the resultant plumes. And the way that she's broken down this problem is to take a given wind direction, southwest winds, northwest winds, southeast winds, and then deflect the wind direction by several degrees, positive and negative, away from that oncoming wind direction. And so she's looking at the sensitivity of the plumes to variations in the wind direction. And what you see here is that for Brooklyn, there's relatively, and then the y-axis is the degree of overlap between the plumes. So if you take a wind coming from the west, you deflect it 2 degrees this way, 2 degrees this way, you compute plumes based on that wind direction. How much do the resultant plumes overlap with each other? And then you add another 2 degrees, another 2 degrees, and you go through the windrows in that way. So when the degree of overlap drops off significantly, that means there's strong variation in sensitivity to the wind direction of the resultant plume. And so that's what we see here for, in particular, Jersey City and Staten Island, the red and the green lines, which are located here, very close to the water. There's, for virtually every wind direction, basic wind direction, these are the climatological wind directions that we see the most in New York City. For virtually every wind direction, you see strong sensitivity for these 2 release sites, Jersey City and Staten Island. And when she analyzed it more, it really is about the proximity to water and the plume transport over the water, creating much more variation in plume outcomes. She also spent some time looking at visualizing these different plumes and the degree of overlap compared to the standard NATO protocol for when you have a release site, you draw a triangle basically downwind, and that is what you use as a hazard area to evacuate. Well, how does that compare when you look at different plumes resulting from different wind directions and different boundary layer conditions? That was an aspect of the work as well. But what clearly emerged is the sensitivity of the release site to the water, and she linked the HPAC, this transport and dispersion tool, to the COAMPS simulations I showed you earlier, and looked at the impact of urban aspects on plume transport as well. I'm going to shift gears and show you another application that we did a while ago before the incident in Japan of the nuclear power plant release. We had been using Tokyo as a case study to look at transport and dispersion applications of a COAMPS ensemble. So I'm just going to show you a few slides on this, and then move on to a few other highlights that I think might pique your interest. So this was a configuration I did with my colleagues at the Naval Research Lab. That was Teddy Holt and Craig Bishop. And we nested with 4 nests using COAMPS down to 1.67 kilometer resolution for the Tokyo Bay area. Tokyo is right here. And what we wanted to look at were 2 different types of physics perturbations. We wanted to examine the sensitivity of transport and dispersion plumes to aspects of the urban parameterization and the specification of sea surface temperature. So we did a series of ensembles, 21 members for this period of time in 2005 with a data assimilation cycle. And we did an offline coupling with the Navy's ocean model, sea surface temperatures. And our perturbations consisted of the following. We perturbed inputs to the urban canopy parameterization, including building height and anthropogenic heating. And we included perturbations to sea surface temperature by doing something very simple and basic, which is time lagging the SST that's given to the weather model. And then we did passive tracer continuously released at several different sites in the domain. And I'm going to show you a couple of results from this that struck us. And one of them is the relationship of the sea breeze front to the city, the urban area, and the ensemble makeup. So this was in the afternoon, the sea breeze front kicks in, and it's a very clearly delineated line between the incoming cooler air and the adjacent warmer air coming off of the city and propagating toward the north. So what we saw is that when you define the location of the sea breeze front, the spread of the ensemble members is quite broad and covers a large area of where the ensemble of all the members think that the sea breeze front is located. So we identified a sensitivity to the location of the sea breeze front using this perturbation scheme for the ensembles. We also identified regions where there's the largest variance, and those occur, a variance in 2-meter air temperature, and those occur predominantly in urban areas, this is Tokyo, and in coastal regions, so high sensitivity there to variations. We, in terms of parsing the urban variations, we looked at, we compared 2 different members, the control member and the member of the ensemble that had increased building heights. And that led to, building heights leads to a deeper boundary layer, more mixing in the vertical, and less contaminant deposited near the ground, or a smaller dosage footprint near the ground. So these are some of the sensitivities that came out of the study. Also looking at the control versus SST that's lagged by 9 days, shows for this particular cross section going from here to here, looking across this direction, we're looking at height through the boundary layer. The transport of the plume has a very different structure. It's much more spread out in the control than when it has a preference for orientation and it's going this way to the west, compared to when it's spread out and going to the west and east in the control simulation. And this, yeah, this was there was a control by the terrain, and the we think it's what we've seen before when we've linked NIHOPS to COAMPS. We've given COAMPS the SSTs from NIHOPS. The upwelling centers, cold and warm pools along the coast can have an influence on the wind speed and direction. And we've seen that before when we've given these higher resolution SST fields back to a weather model. So this kind of encapsulates some of our conclusions from that study, which this is the envelope of the ensembles for these continuous releases. And you see this tendency to go toward the west before the sea breeze kicks in, this tendency to go toward the north after the sea breeze kicks in, and the strong sensitivity to location of the release in Tokyo versus offshore. And the ensemble framework gives a way of quantifying the uncertainty and looking at how individual members performed. So in this particular set, the members that had the increased anthropogenic heating improved the skill, and increased building height improved the skill of the ensemble members. So there's lots of other things you can do. You all know this, you're entering into or well along the way of doing ensemble studies. There's a lot that can be done in post-processing, bias correction, but this was just an initial foray looking into the impact on transport and dispersion of these sort of ensemble simulations. Yeah, yeah.
Yes, you have shown sensitivity given the choice of the perturbations you have.
Yeah.
But have you evaluated how realistic these perturbations are? I mean, what were they based? I understand what they were based on in terms of what you perturb.
Yeah.
But the amplitude and the correlation between the different, especially with physical fields, okay, the height of the building is not related to the distribution of errors in sea surface temperature, of course. But in principle, the perturbations that go into the ensemble have to be based on some estimate of expected uncertainty.
Yeah, so I think that,
and I don't mean just in terms of the expected sources of uncertainty, but also in terms of the distribution of that uncertainty.
Yeah, I think that's partially manifest in the spread skill score, that by increasing the spread skill relationship, that you're showing that the ensembles are creating more skill. There's certainly more that can be done in terms of a smarter choice of the perturbations to better sample the, yeah, absolutely, 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 absolutely.
For any application. Very little work has been done in that domain. How to actually define truly optimal perturbations that really represent the uncertainty of our knowledge of whatever is influencing the forecast.
Absolutely.
It's a very nice study.
Absolutely.
I mean, I have no objection, but
absolutely.
Pointing out that there is
Yes.
more to do.
Yes.
For the exact same case, you can repeat the study addressing this aspect and have new insightful results.
Right. So, you know, one thing we didn't do was, what if you just use an SST derived from an optimal interpolation from basically satellite observations? You compare that to SST from a coupled model. You compare that to SST from an uncoupled model. These are more refined variations that could be included in the ensemble. Absolutely. Now for something a little bit even more different. So one of the challenges is really the way that the contaminant can move between buildings and interact with the urban landscape. And I did a few studies related to trying to quantify aspects of the urban morphology's impact on contaminant transport. So this is an example using a large eddy simulation model, computational fluid dynamics model for this city is for Washington, D.C., which has relatively flat buildings capped at 6 stories, broad boulevards. And for a release site here, we're looking at concentration, 18 minutes for a hypothetical release, hypothetical source. You can see a lot of interesting aggregation of the contaminant behind buildings in various parts of the city. And what I wanted to do was understand better the impact of the cityscape on these patterns. And so I looked at Washington, D.C., and this is showing you two different outcomes from two different release sites. So this is the near the ground dosage, so time integrated concentration emanating from a release source right here at this location, and this one is showing you a release site here at this location. And you can see when the release site is closer to the boulevard, you get transport down the boulevard. When it's more in the weeds or in the middle of the buildings, you get a lot of clustering of the contaminant back into the streets and neighborhoods off the boulevard. Chicago has much more densely packed buildings, taller buildings than Washington, D.C. This is the Chicago River. So this is, again, comparing two different release sites. For release site 1, you get some contaminant transport down the Chicago River. For release site 4, you get a lot of aggregation of the contaminant adjacent to the buildings and some filtering through the buildings.
Is the river actively water?
It's not, it's just a surface, but it's a flat surface. So it's going to act more or less like a road, a street.
But it's not interacting with the atmosphere.
No, and that would be another nice thing to be able to add to it. As we saw for New York, having, you know, the stability of the atmosphere over the water makes a big difference in transport patterns. So what I did was want to examine how that very refined footprint of the contaminant from a large eddy simulation model, how that compares with the footprint of a contaminant that would come out of the standard plume transport model, HPAC. So for identical release scenarios, I quantified the degree of overlap between SkiPuff, that's the module within HPAC that does the plume transport calculations, and FAST3D, which is the urban model or the CFD model. And so looked at short-term near-field, near-surface releases and comparing the cities of DC and Chicago. So I looked at release sites arrayed along here for these two different cities. The CFD model itself has 6-meter resolution in the horizontal and vertical and uses a 1-meter resolution building database for the cities. So this is an example of some of the results. So this is for SkiPuff for HPAC. This is the Plume model that's used as the operational capability, which has now developed an urban module, like an urban parameterization that's not represented in this version of HPAC. For Washington, D.C., same release site, this is what you get when you use that high fidelity CFD model. And I wanted to look at ways to quantify the degree of overlap between these two different resultant plumes.
In some of these pictures, the one top left, looks like the building are not.
Building is not, the building is not, this model doesn't take in the city landscape. So you run it like the land is flat. But it's the shape of these plumes is what are still given to evacuate urban areas.
Oh, sure. But in the other case,
this is a building aware model. This is simulating the flow around buildings with a 1-meter building database. This is a 6-meter resolution model. This is a Gaussian plume model. And this is for Chicago. So this is what we're going to compare are these two different shapes resulting from different release sites, these two different models in these two different cities. So one way to do this is to use a measure of effectiveness, which looks at, this is, I'm going to talk you through how this works, is for a given plume, this is this nice oval shape that's produced by these sort of transport and dispersion models. So this is the ski puff, this is the large eddy simulation model. So you can compute the area, and then you can compute ski puff minus 3D minus ski puff, and you can extract the area of overlap, or how common. If you put all this together, so the columns are two different specifications of the boundary layer, but we're looking at the same thing in each column, which is 12 minutes post-release, 18 minutes post-release. And we're looking at the contaminant footprint and the degree of overlap. And in this plot, the X and the Y axis. So it's you can see it here normalized. And along this diagonal, the plumes share, the plumes are the same size, and the degree of overlap varies. So if you're up here at 1,1, you have exactly the same plume in the same area covered. If you're in this quadrant, then the LES model predicts a smaller area than ski puff. And you're in this quadrant, then Fast3D predicts a larger area than ski puff. So ideally, you would want convergence in your different models. You would want your models are doing similar things. But what you see here for two different specifications of the boundary layer into the model is that there's significant spread between Chicago release sites. So the diamonds are Chicago, and the circles are Washington, D.C. The red circles are Washington, D.C. And the release site is given with the number written in the center of these shapes. So one of the takeaways from this is, for this particular specification of the model, input and source term, there's a stronger clustering of release sites outcomes for DC compared to Chicago. So you get much more variation in the plumes that come out of the Chicago simulations, tall buildings clustered close together, compared to Washington, D.C., which is relatively flat, and the plume convergence is higher. Regardless, there's an interesting amount of discrepancy between the plumes, and for Washington, D.C., Fast3D is predicting a larger area, more spread in a flatter city with the LES model, as the contaminant is able to move through the city. Okay. Of course, we were just looking near the surface, but this really is a 3D problem, and so there's lots of vertical transport as well, and it's very nice to visualize these type of models, because you can see the impact of the contaminant across a whole city. We've had a lot of focus on New York, and one of the reasons it's different is that even Midtown, which I told you, it has a lot of tall buildings concentrated in one area. It's still actually pretty corrugated. There's tall parts and shorter parts, and the average building height is 53 meters, but the standard deviation is about the same too. So New York, you would expect, would have maybe even more complicated transport patterns than Chicago or DC. So that's one of the things we set out to determine when we did a tracer release experiment in Midtown that was funded by the Department of Homeland Security and Department of Defense. I'm just going to show you a quick clip about that. Can you hear that?
You can't see it, you can't smell it, you can't taste it, but government scientists were really interested in it today.
They released harmless gases, as you know, at 4 locations to see how fast and how far chemicals would spread in the event of a terror attack. Kathy Hobbs is live in Midtown with more on this 3-week experiment. Kathy.
And Kathy, this was all about preparing for the worst case scenario. The testing today to determine not only what would happen should there be a chemical attack here in New York, but in any large city across the country. Like the terrorist attacks of September 11th, New York City's crowded streets and busy subway system make it a prime target for terrorists looking to unleash a chemical attack. Preparation for that scenario played out in the streets of Midtown today as government scientists released a series of doses of harmless gases into the air to determine what would happen during a real-life emergency.
We can see we've released 2.5 cc's or milliliters in the first two releases, and we'll release another 1.2 in this release, and it'll do that over half an hour.
The gas is released for several hours today outside landmarks like Rockefeller Center and underground in the city's subways. The purpose to determine how fast and how far chemicals would move through the city during an attack.
Our goal is to better understand how airflow moves in the urban canyons, especially deep urban canyons like we experience in Manhattan.
With tracing devices placed on buildings and vans like this one parked throughout the city,
Writing down what I see.
those working on the government-funded project took diligent notes they hope will help make a difference should there ever be an actual emergency.
We need documentation as they see the material and they document it as things go along so that we can put the story together afterwards.
And from here, the testing will continue. There will be 5 more testing days over the next 3 weeks. Live in Midtown tonight, Kathy Hobbs, WB 11 News at 10. Peter, Heidi, back to you.
So that was the largest urban tracer release study in the US to date. And we got a great deal of data about transport patterns in New York City, and it's been very helpful. But we also need to keep doing more of those type of studies. They're very valuable. So one of the ways these type of models are used, the models we've been talking about, is when there are accidental or intentional releases into the environment. And one of those occurred in Japan with the Fukushima nuclear power plant crisis. And I was contacted by several different groups to help them understand better what were the risks to their industry. I was contacted by some shipping companies, some ports, other places that were not able to gain access to information that would help them make strategic decisions about how to continue their business operations when there's radiological elements raining out of the sky. And so I was motivated to connect with the wider community of people who were doing these type of simulations. We were doing some input for the Navy for some of this work, and understand better what was happening at the decision-making level and how these models were influencing decision-making. So there was the tsunami, the power went out at the nuclear power plant, and that also shut down the reactors. The reactors were inundated with water, and there was a source release into the environment that continued episodically for many days. There was the impact on the environment in several different ways. There was the immediate release into the atmosphere that rained out down onto the ocean. But there was also release into the atmosphere that deposited in the rivers and the mountains of Japan. So you had riverborne transport of radiological elements that made their way to the coastal ocean. You had land deposition, but you also had release of contaminated water into the adjacent coastal waters at the site of the plant. So there were multiple pathways for contamination in this area. And there were several different groups that became involved. The International Atomic Energy Agency commissioned CNRS, the French group, to do dispersion transport studies for the coastal waters. NOAA was involved in the airborne long-range transport patterns. Department of Energy and Department of Defense were involved in computing some of the short-term patterns of deposition. And the Japanese, of course, and the French Radiological Agency were also doing their own predictions. So we brought all those representatives from all those groups together at a conference to understand better what were some of the challenges to decision-making using these sort of model outputs and information. And so these are some of the key points that emerged. One was really the lack of any knowledge or data about the source term made making any decisions on plume transport model output extraordinarily challenging. So the Japanese had a fantastic plume model that was hardwired to take in observations of the source term, the radioisotopes at the stack of the plume stack of the nuclear power plant. And so when the power went out and they didn't have those data as a source term, that broke their model. And so when they were able to rewire their model to take a hypothetical or unit release term, and they put it into their Plume transport model, they got a great result, but they didn't know it because they didn't think that they could trust it. And so they passed these model outputs around to all the different agencies, and no one wanted to take responsibility for doing evacuations off of a Plume model that they didn't know if they could trust. So that shows sort of one aspect of the challenges of not knowing if you can trust a model. So you're sort of paralyzed if you don't know what you can do with it. Other groups decided to anchor on worst case scenarios of what's the worst that can happen so we can decide how far we need to evacuate. And as a result, the United States ended up setting their evacuation zone much larger than the Japanese had established based on their best decision making. So there was this discrepancy between what the countries were recommending for evacuation of their citizens. As I alluded to at the beginning when I described all the different ways in which the environment was contaminated by the radioisotopes, all of these linkages between the atmosphere, the ocean, the river discharge, the chemical weathering of the radioisotopes, all of these things were not, there was no model that encompassed all the different realms and the transformations that were happening in the radioisotopes and the depositions. And so there was this sort of stove piping of people who were doing the waterborne contaminant, people who were doing the airborne contaminant transport. And it made it really difficult to think of whole solutions and to see the problem as in a holistic manner. So these were some of the things we drew out of the workshop that we organized. This is an example of a recent potentially airborne contaminant outbreak that we've been having in New York with Legionnaires. And there were source terms and at potential buildings. And there's been a lot of investigation about the airborne spread of Legionella bacteria. Some of this work has really pointed to important science questions related to contaminant transport, related to measuring, related to modeling. And I think one of the key things that's missing to date is to link that with the emergency response and to do an experiment where you're gathering the data and you're doing good science, but at the same time, you're channeling those flows of information to the emergency responders to understand how they take action on those data and on those model outputs. And I think doing a type of almost simulated experiment where you do the experiment, you release a tracer in the urban atmosphere and ocean, and then you ask the emergency responders to go through their process of taking action and potentially even giving them, using their personal monitors. So they all, like the police in New York carry radiation monitors. So if you take those data and assimilate it back into the Plume models, you could get a better prediction of where the contaminant would go. But because that isn't normally exercised, the first responders don't know that that's available. And so the last thing you want to do in a crisis is introduce a new tool or technology and make people adjust to it. So exercising our evolving technologies and capabilities as we move forward with the emergency responders as a collaboration, I think is a very important aspect of advances in this field. I just want to close with a few slides about a system that a group of students have been putting together. For the past 4 years, I've been running the Maritime Security Center at Stevens, which is the Department of Homeland Security funded Center of Excellence. And our focus is, of course, maritime security, but one of the things that a group of students wanted to do is draw together all these different models and data sets for our urban area of New York and put them together in one user-friendly platform with an emergency response orientation. And they called it Magello. So this is using the NIHOPS data for, say, ocean temperatures, but then overlaying it, as you saw on this slide, with where the ships are. This is just basic AIS for our harbor. So imagine you're the Coast Guard and you're in a search and rescue situation. Maybe you want to know what the water temperature is there, so how long those people can be in the water. Maybe there's a situation of you want to know which vessels are nearby so that you could hail them to go and provide assistance at a scene. And so this gives a situational awareness layers. They combined in some plume transport models as well as weather data into this system. These are some of the inputs. We use the NOAM, the oil spill model, some hotspot, a basic plume model, the Defense Department model, COAMPS, as all of these layers, some of the inputs from the NOAA IUS systems. And so this is the type of visualization that we've done with this, what I said before about where the vessels are and along with the water temperature along the Hudson and the East Rivers. This is a contaminant transport pattern from a hypothetical release in Midtown. So you can see how you could draw all this information together to create more than the sum of its parts. I think this all points to, and this is my last slide, really a way of connecting science with society. And Marcia McNutt, who was the head of the Monterey Bay Aquarium Research Institute and then led USGS during Deepwater Horizon, where they were doing the assessments of the output of the oil from Deepwater Horizon at USGS. And then now is the editor of Science Magazine, and will move on this year to be head of the National Academy of Sciences, the first woman to be the head of the US National Academy of Sciences. She wrote an editorial a few months ago calling for the need for a community for disaster science, to bring the best of science from academia, from government together, to be communicating in advance of crises. So again, that you're not just, as some people have suggested happens way too often, exchanging business cards in a crisis. And I think it's a really compelling call for collaboration across the sciences of disaster and emergency response. And I think that you all also have a strong role in that, in the response work that you all have been doing. So I look forward to talking with you more about these ideas. Thank you for your attention.
Just wanted to ask if the urban air quality model considers the weathering of the pollutants and also the aerosol